Significant figures. When we measure something, the measured values are never exact. The measurement is only known within the limits of the experiment or the measuring equipment. For example, if we're measuring length using a meter ruler, the exact length of an object, if you really look down to it, will depend on individual atoms, but our ruler can't measure that distance. Let's say that we're going to measure this purple bar here, and we're going to use a centimeter ruler. And you can see the purple bar when we're measuring it. The length of it lies somewhere between the 4 and 5 centimeter marks. Now we can have a guess and say it's about 4.8 centimeters, but like I said, it's a guess. Our measuring equipment doesn't allow us to go accurately to that 0.8 or the 1/10 of the centimeter in this case. So because we don't have the equipment that allows us to measure that accurately, we can just say it's 5 centimeters and it's accurate to that one significant figure. I've got these two blue lines on the screen here. If this purple bar was anywhere in this range, from here to here, we could also say this is 5 centimeters. In terms of engineering, this is called a tolerance, and we would say it's 5 centimeters plus or minus half the most precise division, which would be half a centimeter. So 5 centimeters plus or minus half a centimeter. Looking at another example, but using millimeters in this case, we've got this purple bar that we're measuring, and we can see that it doesn't quite line up with the 113th millimeter. It's just slightly short, but we can't say it's 112.8 millimeters because our equipment doesn't go to that level. So what we say is it's 113 and accurate to 3 significant figures. So significant figures allow us to know the accuracy of our measurements. So I'm going to go through a few examples, and you'll be able to see as we do this how many significant figures that different numbers have. So in the first example, we've got, looks like pi, 3.14159. If you count up the digits, there's 1 before the decimal and 5 after the decimal. Now, all of these are important and they describe the accuracy of our measurement. So in this case, we've got 6 significant figures. In the next case, we've got the number 1000. And if we were measuring something, it looks like this number could have been rounded. So we're unsure of the accuracy of this measurement. So with the number 1000, the 3 zeros just indicate the magnitude of the number, where the 1 is the most significant part of this. So in this case, we've got 1 significant figure. Now in the next example, we've got a decimal after the 1000, and it's 0.0. Now this indicates that it's accurate to that 0.0 or that decimal. So that's important. So what that means is that in this case, we know that we've measured that accurately and we have 5 significant figures. All right, in this case, we've got 3 zeros after the decimal point, and again, they just indicate the magnitude and they're not important. What is important is the 3-5 at the end, meaning 2 significant figures. In the next case, it's a similar number, but this time we've got the 350 at the end, and this case we have 3 significant figures, else why would we have that 0 at the end? So it's indicating the precision of our measurement. With the 1006, we know that we've measured accurately enough that the 6 is important. So the zeros between 2 integers are important, meaning this one has 4 significant figures. All right, the next 3 show the importance of that decimal and the precision of the measurement. So you can see with the 560, that 0 at the end is not important because it could have been rounded. The 5 and the 6 indicate the precision of the measurement. With a decimal, never see this written like this, but it does indicate that the measurement was a little bit more precise, meaning 3 significant figures. And the final one, we have 4 significant figures. When working with numbers, the accuracy of our result can only be as good as our least precise value. I'm going to go through addition and subtraction first. So let's say we're measuring around a soccer pitch with a trundle wheel, and we might get 280 meters. So it could be 280 or all the way up to 280.9. We don't know because it hasn't clicked over. Now let's say we're performing a calculation. We want to remove the distance between the goalposts. So we're going to measure this though, not using the trundle wheel, a little bit more accurate, using a ruler, and we measure 7.3 meters. So we can perform our calculation as seen here, and it's accurate down to the decimal point in the order of 10 centimeters. But since when we were measuring the distance around the pitch, we were only able to measure accurately to 1 meter, our final answer can only be accurate to 1 meter. So we have to do the rounding, and our answer is 265 meters in this case. So now let's look at a case of multiplication and division, and it's the same. Our final answer can only be as accurate as our least precise measurement. So if we wanted to calculate the area of the pitch, we measure the length using the trundle wheel to 95 meters. We choose to measure a little bit more accurately with a meter ruler to 45.0 meters. Now the area is calculated as 4,275 meters squared. Now, since the length was measured to 2 significant figures and the width to 3 significant figures, our answer has to be presented to the least precise measurement, being 2 significant figures. So we have to round our 4,275 to 4,300 meters squared, and we put the 2 significant figures in brackets to indicate the precision. Calculation question for you now. Assuming a circular orbit, calculate the distance the moon travels around in that orbit in 1 rotation. So we have to use the formula for the circumference of a circle and provide your answer in the correct significant figures.